So now that we know how to define this Taylor series, which is defining this function as a power series where the coefficients of the power series are the zeroth derivative, the first derivative, second derivative, and so on, divided by k factorial. So the kth derivative divided by the k factorial at that particular value. We're actually going to put it into practice and find some Taylor series. Now the first Taylor series we're looking for is the f of x equals e to the x about x equals 0. In other words, this is going to be a Maclaurin series, named after the person that thought of it. So Maclaurin series. So if we're going to build a Maclaurin series for this, then we need to be able to find all of our derivatives because we're going to need the derivatives in order to find the coefficients. Okay, so let's start. We need f of 0, so I'm going to put that right over here. F of 0, which is e to the 0, is 1. And then now I need to find the derivative of f prime, or excuse me, f of x, f prime of x, which is e to the x. This is everybody's favorite Maclaurin series because it's so easy, because the derivative of e to the x is e to the x. So this is 1. And the third derivative, oops, wait, the second derivative. I was jumping the gun. The second derivative is e to the x. So the second derivative at our a value is 1. The third derivative, there we go, is e to the x. And I'm just going to stop there because we can see how this is going to go, right? This is going to work this way. So now if you look at the formula says that the Maclaurin series, it's right there, there's the formula, is going to be from k equals 0 to infinity, the kth derivative at 0 over k factorial times x to the k, right? So that's the formula. Now how's that going to work for our particular problem? Well, obviously it's going to be a series. And then we're going to have it be fk of 0. But in this case, it's always 1. I mean, if you look at the kth derivative at 0, it will always be 1 no matter what. That's why e to the x is everybody's favorite, because it's so easy. And then it'll be divided by k factorial. Right, so that'll change for every piece of this. And then it'll be x to the k. Oh, I better leave space because we don't know the interval of convergence. So we're going to have to find that. So I'll leave some space and be able to put in my interval of convergence right there in just a second. So let's go find the interval of convergence. Let's do it down here. Okay, so let's do the ratio test. Everybody loves the ratio test. It's so much fun. And not only that, there's factorials in this. I mean, we all learned that when there's factorials involved, use the ratio test. Okay, so r is equal to the limit as k goes to infinity. And then remember how it goes. It's a sub k plus 1 divided by a sub k, right? So our a sub k plus 1 is really x to the k over k factorial. Right, so it's x plus, or excuse me, x to the, I'm doing this right, not x plus 1, x to the k plus 1 over k plus 1 factorial. And then we're going to divide that by x to the k over k factorial, because that's what a sub k is, right? A sub k is x to the k over k factorial. Okay, so that would be the limit as k goes to infinity, x to the k plus 1 over k plus 1 times k minus 1, dot, dot, dot. Just reminding everybody how those works. And k factorial is k minus 1, k minus 2, etc. over x to the k. Well, I wrote it out like that just to remind everybody that all of these are going to go. Leaves you 1 left over here and a k plus 1 down there. And then the x to the k and the x to the k plus 1 is going to go and leave you just x, right? X to the 1, if you want to think of it that way, right? Because k plus 1, take away k is 1. Okay, so that means that I'm taking the limit as k goes to infinity of x over k plus 1. Well, that's the limit, so that's absolute value of x times the limit as k goes to infinity of 1 over k plus 1. Okay, so the absolute value of x is just the absolute value of x. I could pull it out because it has no k in it. K is not involved, so it's not really part of the limit. So that's why I was able to pull this out. This is 0 for all x. That's why this is going to converge for all x. That's our interval of convergence. Because 0 times whatever x is 0. So my interval of convergence is actually negative infinity to infinity. Now, let's use what we just did to come up with the one for e to the negative x. So let's think about this. We just determined in A, we determined that e to the x is equal to the power series x to the k over k factorial from k equals 0 to infinity. Right? We just determined that. And then it was for negative infinity to infinity. Okay, so then how can I use that? Well, if you look at the one we're doing now, I want e to the negative x. So what's that going to mean? That's going to mean will be equal to, it's still going to be a power series. And then instead of x, I'm going to put in negative x. Right? I'm using the term I already know. And that would be, if you want to write it slightly differently, it's negative 1 to the k, then x to the k over k factorial. It would also be for negative infinity to infinity, and the reason is that the ratio test would be exactly the same. When you look at the ratio test, all that would change would be a negative 1 to the k, but that will disappear because of the absolute value. So this is literally the exact same ratio test as part A. So let me circle this, or box it, I guess. And we can just make a note. It's the same ratio test as A. So we don't have to show it. We just did it. Now, how will we modify that for this one? Well, keep in mind, this is still the formula for e to the x, right? So h of x would be x to the 4th e to the negative x cubed. So that's taking the e to the negative x. So this is x to the 4th times, and then the sum from 0 to infinity. And then instead of x to the k over k factorial, I would have negative 3x squared to the k over k factorial. Right? I'm substituting this value right here in for x, right? Where it used to be just a regular x in there. Okay, so let's break that down just a touch. This would be equal to, let me think, an x to the 4th out in front, and then I'm going to have that sum. I'm going to break that negative out of there. So that's negative 1 to the k, and then, or I could say negative 3 to the k. I might as well keep the number with it. So negative 3 to the k, and then it would be x squared to the k over k factorial. And then there's an x to the 4th out here, so I can put that inside. And I can say, okay, that's the sum from 0 to infinity. That doesn't really change. And it'd be negative 3 to the k, x to the 2k, because you'd multiply, 2k plus 4 for out here, over k factorial. And then the interval of convergence would still be negative infinity to infinity. Because if you think about what would happen here, you'd have x to the, it'd be some modification of this. So, 2k plus 5 and then 2k plus 4, and then they divide. So it wouldn't make any difference. So the ratio test would work out to be the same. So it'd be for negative infinity to infinity. Again. Because what the modifications we're doing are not really changing the ratio test. So it's the same, I'm going to say same-ish ratio test as part A. It's not exactly the same, but they're very, very close. And just so you can see what's going on in Desmos, just to make it true so you guys can see it. E to the x is my function, which is red. That power series is that power series we developed in part A. And you can see as I let my top value of my series get larger and larger, it's covering completely, that power series is covering that function, and it will keep going like that. That's why it's from negative infinity to infinity. And you could actually play around with this. I'll post this for you, but you could play around with this by changing up your function to say e to the negative 3x squared, and then playing with your power series and seeing that it doesn't matter how large you let it get, it's still going to be matching, right? It'll go from negative infinity to infinity. That's what it means when we say that e to the x is equal to that power series. They're completely covering each other, and this particular one is actually working for all values of x. All right, last but not least, what about if we go from x equals negative 4? Okay, so remember how the derivatives all worked. So if I have, let me just go through them. So if I have k of, well, let me do k of negative 4 really quick. So k of negative 4 would be e to the negative 4, which is e to the 4, right? And then I have k prime of x, which would be negative e to the negative x. K prime of negative 4 would be negative e to the negative 4, which is negative e to the 4. And then k double prime, second derivative, would be e to the negative x again. And so the second derivative at negative 4 would be positive e to the 4 again, right? So it's going to go positive e to the 4, negative e to the 4, positive e to the 4. If you want to take a bet on the next one, it'll be negative e to the negative x. So the third derivative would be negative e to the 4 again. And it would just continue in that vein. So you can see what's happening. E to the 4, negative e to the 4, e to the 4, negative e to the 4. Why did I do that? Well, because if you look at the formula, it involves x to the k over k factorial, and that only happened because of our derivative. So if we go back to the basic formula says that you're going to go from k equals 0 to infinity. You're going to do the kth derivative at negative 4 instead of at 0, which all the other ones were, over k factorial times x minus a negative 4 to the k. Okay, so we knew the k factorial was there. We saw that before in our Maclaurin series. This is going to be x plus 4, not too bad. But what we need is a pattern for finding that kth derivative, and that's what we're using right here. So we can see that the kth derivative, f kth at negative 4, would be equal to negative 1 to the k. That'll get you your alternating. Zeroth derivative is positive. First derivative is negative. Second derivative is positive. So if I use k, that'll work, right? Because this is the zeroth derivative, the first derivative, second derivative, third derivative. So the odd numbers have to be negative, and the even numbers have to be positive. And then it's e to the 4. So that's what I'm going to substitute into the formula. So I'm going to say, okay, it's k equals 0 to infinity. It's the kth derivative, which we now know is negative 1 to the k e to the 4 over k factorial x plus 4 to the k. And still this one is for negative infinity to infinity. It's very similar to the ratio tests, similar-ish to the ratio test we did originally. What would happen is you'll have x plus 4s divided by x plus 4s instead of x's divided by x's. Oh, sorry. I have to find our test. Here it is. So instead of, all that's going to change is that it'd be x plus 4 to the k plus 1 over x plus 4, but it's not really going to change it much, right? So it's just going to have a center at negative 4, but it will still go from negative infinity to infinity. So we can say this is a similar-ish. They will not always be the same like this. We're building off of one that we already know. Ratio test to part A. Of course, if this was a worksheet or something, you might actually have to show that ratio test. But for our purposes here, we're not going to redo the same ratio test over and over. So real quick, we found one Taylor series, a Maclaurin series. We did the ratio test to find the interval convergence, and then we're manipulating it and playing with it. And one of the reasons the intervals worked out so nicely in all these is because they were all negative infinity to infinity. If it was something else, you might actually have to start doing a little bit more work there.